Recording started. Okay, so chapter 10 is going to look at hypothesis testing for a single sample. So for dual credit, the only markings I'll allow you to have on your formula chart, that chart that was on top of your packet that I gave you, the only markings I'll allow you to have on it is where you circle one population or two populations. And that's right there on the top. Can I borrow the chart for So if you're wondering where am I talking about, up here it says one population. You can circle it, you can highlight it. Because this side would be one population. The other side says two populations. So that way, when you're looking at this, you're like, okay, how many populations do I have? I have one. Okay, I'm going to be on the one that says one population. Chapter 10 is going to be the one population. Then we'll get to chapter 11. That's when we'll be on this other side with two populations. So, you will not need that for today.
Yes, sir. When is our next test, you say?
So y'all's next official test. You can't see. Can you do me a favor? Because I can't see that far. What does it say on the statistics calendar for dual credit test number 4? I think it's that week right before Thanksgiving.
That long?
So I think it's that week before.
Teachers, at this time, downstairs only will proceed with the fire drill.
Which one?
Again, downstairs only.
That's y'all's next.
Proceed with the fire drill.
On November 17th for dual credit.
I'm good with that.
Now, when AP takes their next test on the 6th, I'm going to pass out what I'm calling a project. For y'all, it's not really a project, it's a really wordy packet of multiple choice questions. Like you're having to analyze different things, and it's a thing that the state requires us, all colleges, to do. It's 3% of your grade, not much. I mean, it's just, we've got to do it, so it's like, I'm going to give you a grade for it, but it's not a big part of your grade. Like 20 multiple choice questions. Okay. So that's what you will start. You know, y'all can even, on that one, if you don't finish it in class, you could take it out. I mean, you just put all your answers in Blackboard, so Blackboard could grade it real quick. Anyways, chapter 10. Hypothesis testing using a single sample. So what hypothesis testing is, it's basically, it's like it sounds. It's a way to test a set of hypotheses. So if you think back to science, you're like, I wonder what happens when I mix these two chemicals together. You might, before you mix them, say, I think this is going to happen. And then you do the experiment, and you're like, yes, it happened, or no, it didn't happen like I thought. That's what we're doing here, but we're using math. We're doing statistics. So, yeah, that's kind of what hypothesis testing is. We're using the data from a sample to either back claims or refute them. And really, well, before I say this, does anyone play the game Among Us? I don't play it, but from what I've heard, it's like,
You should play. I'm like,
I don't even, y'all can tell me if this is even accurate. From what I've gathered, it's like, you go around killing people, and then they have to vote on who they think killed the person.
Basically, if you play Mafia,
No, I don't really play video games.
No, it's like a party game.
Yeah, it's like a party game.
Yeah, like everyone like has to look down and close their eyes, and like some person's a mafia,
Oh, yeah.
and then this person who's a cop has to figure out who the mafia is,
Ah.
and there's a person who's a nurse who has to prevent somebody from dying or whatever.
And then there's the doctor who can heal someone.
Yeah,
Ah.
yeah.
Oh.
I like,
So, when you play those games, though, everyone is really a suspect, right?
yeah, everyone's a suspect.
Everyone's a suspect. So that's kind of what's hypothesis testing. You're never really happy if you can't reject the null. What we're going to learn is called the null hypothesis. It's like, I can't reject it. I don't think it's right, but I can't say it's wrong. So we never say, okay, I agree with it. It's wrong. But can we prove it's wrong, or do we just have to live with the fact that we think it's wrong? We just can't prove it. So that's essentially what we're doing here. Now today we're just going to set up these hypotheses. We're not going to actually solve any problems mathematically, so there won't be any math involved today. We're just setting up the problem. Okay, so in statistics, a hypothesis is a statement about a population characteristic. So let's say we have this problem: sharing prescription drugs with others can be dangerous. Is this a common occurrence among teens? Or maybe we have another question. They say the average starting salary for students graduating with a bachelor's degree is $48,000, roughly. Is this true for your college? So how do we answer these questions using sample data? Well, we've got to come up with a method to where we can test whether their claims are true or not in our hypothesis testing. So in chapter 9, we said, oh, well, we're 95% confident that the real value is within this range. If it's not in the range, we said, oh, well, it's probably not likely. Well, that's one way to do it, but another way is with this testing. So we're going to use sample data.
Thank you, everyone. You may enter the building.
We will use sample data to test some claim or hypothesis about the population characteristic to see if it is plausible. To do this, we use a test of hypotheses or a test procedure. So what is a test of hypotheses? It's a method that uses sample data to decide between two competing claims, which are our hypotheses, about the population characteristic. So is the value of the sample statistic some random occurrence due to natural variation? Think back to our cans of soda. You know, we said, and we even looked at confidence intervals that said they're not exactly going to be 12 ounces. They may be 12.1, they may be 11.9, but on average we hope they're 12. So is it a random occurrence due to natural variation, or is it a value that would be considered surprising? You opened a bag of potato chips and there was only one chip in there. Wouldn't be surprising. Would you be happy though with it?
I think I would. Honestly, I'd be like, this is so cool. Look at my bag of potatoes.
It's only cool if you like know there's nothing in your life. It's just you trade for the next one.
We have to play it, right?
I knew it was empty. There's nothing rather than
I don't know. I feel like I almost would be okay with it? Because it's like the saying goes, you can never eat just one, so if there's one in there, that's all you can eat.
That is a good
Yeah.
point. It just depends on how hungry I am. And you wouldn't want to eat that.
But yeah, you'd want that bag, because then you get the taste, and then that's all you can eat. Okay, so if it's not likely to occur, that means we're out in the tails of our distribution. So let's set up the formal structure for these hypotheses. So these tests are based on something called reductio ad absurdum, form of argument. Essentially what that's saying is we make an assumption and then attempt to show that that assumption is an absurdity or a contradiction. Therefore, it's wrong. So a common one that I did it with third period, they bared with me. I'm not gonna put y'all through the misery of it because it's more theoretical. But a common proof, like your elementary proof by contradiction for math, and you don't have to write this down, this is just an illustration, says that you have to prove the square root of 2 is irrational. So just a rational number is where you have a and b, a divided by b in most reduced form. And I said, okay, I have to prove it's irrational. Well, you know what? Let's suppose it's rational. I don't care what you say. I'm going to say it's rational. Then mathematically, you could work through it and say, okay, well, if it's rational, that means I can write this as a square root of 2 equals a fraction. Then when I cross multiply, I get that a squared equals 2 times b squared. But then that means a and b have something in common. But they can't because this is supposed to be reduced. So this would be a contradiction. Therefore, my statement that I said, let's suppose it is rational, is absurd, which means it must be irrational. Essentially, you're contradicting yourself is what you're doing.
Just saying it's irrational, you're saying it can't be irrational.
That's right. Yeah. You weren't saying that you didn't prove that it's irrational, you proved that it can't be rational, therefore it must be irrational. That's the whole concept of hypothesis testing. You're not proving your original hypothesis. You're trying to prove that it can't be your original hypothesis.
That's why the confidence interval is so big. Makes a lot more sense.
Yep. On the intervals, we're like, look how wide our interval is. It's outside it, so it can't be a good value, or it's rare. Now, we're doing away with the confidence intervals. We're just running a test, and we're going to get, as we'll learn, I don't know if it's tomorrow or the next day, something called a p-value, which is the probability that we're outside that range. So, yeah. So, hypothesis statements. The null hypothesis is denoted by H naught. And it's a claim about a population characteristic that is initially assumed to be true. Notice it says population. For hypothesis testing, we are not concerned about the sample. We're concerned about the population. The alternative, denoted by H sub A, is the competing claim. And sometimes when I'm joking around, instead of saying H naught and H sub A, I just say ho ha. Ho and ha. What's ho, what's ha? Almost like the Snow White. Hey ho, it's off to work we go. So usually we're trying to determine if the alternative is believable. So we start with the null, yes, but what we're really wanting is to show that the alternative is the believable claim. So to determine what the alternative hypothesis should be, we need to keep our research objectives in mind. Think about going to the store and buying that can of soda. Well, the manufacturer says it should be a 12-ounce can. When would you be mad? If you bought it and it was 10 ounces, or
11.9.
well, you'd be mad after 11.9.
11.99999.
So, in that case, you would want to test, is it less than 12? That's when you'd be mad. If it was more than 12, either your can got bigger or the can exploded. Because usually there's not much room for error in those cans. I mean, just drop one and watch how quick it explodes. But the hypothesis statement is always about the population, never about a sample. Always population, never sample. We have to get a sample to use it to test. But we're concerned with the population. So the formal structure. Typically, one assumes the null hypothesis to be true, and then one of the following conclusions are drawn. Either we reject the null, which is equivalent to saying the alternative is correct or true, or we fail to reject the null, which is equivalent to saying that we have failed to show there's enough evidence for a statistically significant deviation from the claim. So we either reject or fail to reject. Never do we accept. We never say, oh, I accept the null. No, you fail to reject it. Remember, always stay suspicious. So, even though we fail to reject, we're not saying it's true. We're just saying we can't prove otherwise. Okay, who wants to be a volunteer? Let's say you're going to go up for a murder trial. Who wants to be the defendant? Will? Okay. So, Will, let me ask you this. When you go on trial, what do you want us to start assuming?
Until proven guilty.
That you're innocent until proven guilty. Okay, so what would our null hypothesis be? You didn't do it. That you're innocent, right? So this is what we want to assume before the trial begins. Will is innocent. You don't want to go in there and have us say, he's guilty, tell us otherwise. Lock him up unless you can prove otherwise. Then you'd come back and say, they didn't give us a fair trial. They didn't give me a fair trial. What's the alternative? He's guilty. Now, so we're in this trial. he starts off innocent. Would it be valid if they gave the evidence and they were like, well, we're not 100% sure that he killed the person. We think he did. The evidence doesn't say 100%, but since we think he did, he's guilty.
That wouldn't even necessarily fair.
That wouldn't be fair with it. What do you have to have in a trial before you can say they're guilty?
At that point, speculation. You have to have concrete evidence.
You have to have concrete evidence. That's right. Same thing with statistics. We've got to have concrete evidence before we can reject the null. So to determine which hypothesis is correct, the jury listens to the evidence, and only if there's evidence beyond a reasonable doubt would the null be rejected in favor of the alternative. Beyond a reasonable doubt. Looks like what?
Looks like I'm innocent.
Looks like you're innocent?
Got away with it.
If there's not convincing evidence, then we would fail to reject the null hypothesis. Now, remember that the actual verdict that's returned is guilty or not guilty. We never end up determining the null hypothesis is true, only that there's not enough evidence to say it's not true. So he probably killed the person. He was just really good at covering up the evidence where we couldn't find it. So therefore, he got away from us. We never said he was innocent. We just said not guilty. So when we make our decision, we're either going to reject the null or we're going to fail to reject the null. Okay, so let's talk about forming the hypotheses. For the null hypothesis, the population characteristic equals the hypothesized value. Our population characteristic could be mu, it could be sigma, it could be p. Notice those are all population based. They're not, I didn't say X bar until just then. P hat, that's sample based. It'll be mu, sigma, p, all the population based. Now, dual credit. We're going to be a little different here. But for y'all, it may be almost in a good way. So, it won't always be equal for y'all. Dang it, I didn't erase the notes from last period. So, I don't want to see any of this. Okay. So for dual credit, it could be equal, less than or equal to, or greater than or equal to. AP, don't write this down. Y'all's will always be equal. But y'all's are always equal. Dual credit, it could be either one of these. You go there. Notice, what do all three of those have in common? They all include the equal portion. They're either directly equal, less than, or equal to, greater than, or equal to. Okay, so that's our null hypothesis. So in one way, shape, or form, we're going to always include the equal case. The hypothesized value is a specific number that's determined by the problem itself. Now, for the alternative hypothesis, there's 3 different options. They're the same for both AP and dual credit. First option is that we're strictly greater than. Strictly greater than. The population characteristic is strictly greater than our hypothesized value. Now, what do you notice about the wording here? If I were to assign numbers to each, or letters to each of these, what do you think you would notice here? They use the same values, the same population characteristic, the same hypothesized value. It's the same. The only thing that will change is our sign. Everything else stays the same. The sign that we'll use is determined by the context of the problem.
There's always greater.
What's that?
I thought you said it was always greater.
No. There's going to be 3 different options here. They can be greater than, it can be less than, or it could be not equal to. Greater than, less than, or not equal to. Yes.
What if both the null and alternative hypothesis are wrong?
That can't exactly happen. If we can't reject the null, then we fail to reject it.
So the null hypothesis is that it's equal to, but the alternative hypothesis is that it's greater to. But what if the value, the hypothesis value is less or greater?
Oh, I see what you're saying. What if you're saying like we're leaving out half of the distribution,
Yeah.
right? Well, it comes back to, for y'all at least, no credit, remember can't have the less than or greater than. For y'all, it comes back to the fact that we have to look at the context of the problem. Like if we're looking at cans of soda, you have to try to think, okay, which way are we looking at this from? Looking at it from the consumer side, they would be pretty mad if you were getting 10 ounces instead of 12 ounces. You would want to test to make sure it's not less than 12. I don't really care about the greater than because no one's going to complain if you're getting free product. Now, flip the script. If you're the manager of the company, do you want to be giving away free product? No. So if that were the situation, then you would want to make sure that you'd probably go with equal and not equal to make sure it's you're happy, consumer's happy, everybody's happy. That make sense?
Yeah.
That's where, when I mentioned you have to look at the context of the problem, that's where that comes in. So the first 2 alternative hypotheses are considered one-tailed tests because we're only interested in what's happening in one direction. Either strictly greater than or strictly less than. We don't care about the other side. The one that's not equal to is considered a two-tailed test because we're interested in both directions. Is it bigger? Is it smaller? We want to know about both directions. So it's considered a two-tailed test. So let's practice writing these hypothesis statements. And this next tip is actually to help dual credit the AP. You can have a brain break or listen, your choice. It doesn't really apply much to you though. Okay, so to figure out our hypotheses, it's a good idea to start with the alternative hypothesis first. If the claim states an equality, then that claim will be the null. Otherwise, we'll write the alternative first. And that's based on what's given in the problem. If we're interested in something being less than 12,000, then that's our alternative. The mean is less than 12,000. The null would be the complete opposite. If it's not less than, it has to be greater than or equal to. Question?
I don't know why.
So start with the alternative, and then once you get that, just take the opposite from the null. Okay, so let's look at an example. So sharing prescription drugs with others can be dangerous. A survey of a representative sample of 592 U.S. teens, ages 12 to 17, reported that 118 of those surveyed admitted to having shared a prescription drug with a friend. Is this sufficient evidence that more than 10% of teens have shared prescription medication? On these examples today, we're not solving anything yet. We haven't learned how to solve anything yet. We're just setting up the hypothesis. Good. First thing we got to figure out is what population parameter are we looking at? What's that?
All things.
People ages 12 to 17. So, in particular, it's the true proportion P of teens who have shared prescription medication with friends.
Why isn't it sample?
Wasn't it what?
Is it not a sample?
Well, our data comes from a sample, but remember when we state hypotheses, we're always interested in the population.
Okay. Gotcha.
So we're just going to say P is what? Well, I want to start with my alternative hypothesis. That's what I'm wanting to prove is my alternative. So what am I really wanting to show? That P is what? P is greater than 10% or 0.1 as a proportion. So that would be my alternative, HA. I don't think I can write on here. Nope. Okay, I'm going to just have to open a new Word document because I have all the answers in this one, so I can't use it. Or I would just give y'all all the answers.
didn't want to.
Well, that's the deal. I don't want to. I don't want to do that. Why would I want to do that?
Learn.
Boom. All my ink is gone, so I can work on here now. Okay, so let's see. What did we say? We said P was equal to what? Well, for our alternative, yes, we did say P, but we didn't say equals. We said greater than 1. Keep in mind, P is the true proportion, repopulation proportion. Of teams who have shared medications. Okay, so if the alternative, and I'm going to do these in accordance to what dual credit has to do. For AP, just remember the null is P equals, that's what it is. Population equals number. So that's all how it's going to always be for y'all. For dual credit, we have to take the opposite for our null. So what's the opposite of greater than? Less than or equal to 1. Like I said, AP is always going to be equal, right there. Yes, y'all for the null, y'all will say P equals 1.
That's a little.
Not a good reason that I like. I mean, during lunch, because third period asked the same question, I looked in the textbook and they still don't really give a reason. No, I feel like you're leaving out stuff. And for this one, that's all we have to do. We're just stating the hypotheses. Some of your questions, that's what you'll have to do. Yep, state them. We're also going to have a question like we're going to do at the end where they'll give them to you and then say, you know, are these valid? And then I think you'll even have some where it's like, they conclude this. So based on what they conclude, did they reject or fail to reject? Yes. I would like y'all to. Yeah. Okay, next one. Compact fluorescent light bulbs are much more energy efficient than regular incandescent light bulbs. You know what an incandescent bulb is?
I've heard of them. I don't remember exactly what it is. That's like.
An incandescent light bulb? What? Yeah, it's just your normal white light bulb that's got that little, you look inside, it's got that little wire that when you turn on the power, it like the wire is what glows. That's an incandescent light bulb. And of course, fluorescent ones are the ones that, as far as normal light bulbs go, they're the ones that come down and they kind of spiral down and then back up. I kind of didn't draw that right, but hopefully you get what I'm trying to. And now they have ones that are LED. They don't have the gas in them. So, anyways, EcoBulb brand, 60 watt fluorescent light bulbs state on the package that they have an average life of 8,000 hours. People who purchased the brand would be unhappy if it was less than 8,000. A sample of these bulbs will be selected and tested. So for one, we're testing the average life. So which population characteristic deals with average? Mu. So let's say that mu equals true mean life of the light bulbs. Okay, so let's come up with our hypotheses. And we want to start, if possible, we want to start with the alternative. So what are we really trying to prove here? What do we hope to prove? That would be y'all's null hypothesis for AP at least. For alternative, what does it say here? They would be unhappy if it was less than 8,000. So here, mu will be less than 8,000. Again, for AP, null is always equal. Full credit. What should our null hypothesis be? Now I've got mu and I've got 8,000. What sign should go in the middle here? Greater than or equal to?
Why is it again?
Y is which one?
Are we supposed to write down both of them?
Yes.
Okay. Can you explain what it means again?
So this first one's our alternative. That's really what we're interested in proving. So it says in the problem that they would be unhappy if it's less than 8,000 hours. That's what we're going to put down as our alternative.
Okay, so the good thing is greater than or equal to.
So the null, which we're hoping, in this
We're
case,
hoping it's that.
that would, yeah. We're wanting to prove the case that they're going to be unhappy. So the opposite of unhappy would be happy. That's going to be the null. So
Alright, I get that.
essentially we start here. Whatever we want to prove here is what's in the problem. And we just take the opposite for the null.
Okay, so it's HO up top and then HA down below?
Yes.
Okay. Thank you.
Mm-hmm. Okay, next one. Because in variation of the manufacturing process, tennis balls produced by a particular machine do not have the same diameters. Suppose the machine was initially calibrated to achieve the specification of mu equals 3 inches. However, the manager is now concerned that the diameters no longer conform to this specification. If the mean diameter is not 3 inches, production will have to be halted. Okay, so what are we dealing with here then? What population characteristic am I dealing with? Mean. So let's say mu equals the true mean diameter of the tennis balls. Okay, so now the top of the next page is actually where they give you the space to write the alternative, for the null and the alternative. Okay, so what's our, let's see, what does the problem tell us? Mu what? Mu equals 3 inches. So which one should that be since they give me an equality? That's our null. What's the opposite of equal to? Less than or greater than, or we could say in one symbol, not equal. So an alternative is that mu is not 3.
So if we're looking for the mu equals 3, then we can put it doesn't, looking at it, it's just a 9.
Yep. Okay, I want y'all to look at the next one and see if you can possibly set it up. And I'll admit this next one's a little tricky. I just want to see what y'all's thought process is. Okay, so what population parameter are we looking for? We're going to want this on the average, so mean, what's mu equal to then? Well, yeah, but in words, like what does mu stand for? True mean weight of the cans of peaches. Okay, so here they're asking about, do the cans of peaches sold by Del Monte meet the claim on the label on average? So let's look at this from the consumer perspective. When would the consumer be mad here? That's right. So notice the real concern would be selling the consumer less than 16 ounces. So what would our alternative be in this case then? If that's our real concern, what would the alternative be? Use less than 16. What's our null hypothesis? For all, yes, that's right. Dual credit, what would the null be? U is greater than or equal to 16. Okay, questions on that one? Okay, on the next one, it says, do 2 brands of light bulbs have the same mean lifetime? State the hypotheses. Well, let's say that mu sub A is the true mean life of bulb A. Mu B is the true mean life of bulb C. So what are we given in the problem? Do they have the same mean? So what does it mean to have the same mean? They're equal. If they're equal, which hypothesis is it? Null. Perfect. So the null is mu A equals mu B. What's the opposite of equal? They're not equal. So the alternative is that mu A is not equal to mu B. Next one. Do parts produced by 2 milling machines have the same variability in diameter? Now we're talking about variability. What population characteristic deals with variability? Standard deviation and variance, yep. So we can either use sigma or sigma squared here. Either one works. I'm going to use sigma. So we have 2 machines here. So the first one I'm going to say is the true standard deviation. I'm going to abbreviate standard deviation here. To do what? Yeah, this is a valid abbreviation for standard deviation. Yep. True standard deviation of, let's see, machine, let's just call it machine A. Then sigma B is the true standard deviation. of machine B. So what am I interested in finding? What's the question asked me? Do they have the same? So what's the same mean? Equal, and which one deals with equal? The null. So I'm going to say sigma A equals sigma B. Then what would my alternative be? Sigma A does not equal sigma B. Yes. So how do we feel about identifying the hypotheses? Easy, hard, has its moments.
That's just a lot of words. The B on the very last one, sigma B.
Yes. Okay, let me go back to the PowerPoint to make sure I haven't forgotten anything. Yeah, we talked about that. Yes, ma'am. Okay, so just a word of caution. When we set up a hypothesis test, the result is either one, strong support for the alternate hypothesis, if we reject the null, or two, not enough evidence to refute the claim of the null. Meaning we're just stuck with it. You may not agree with it, but we're stuck with it. Because there's a lack of strong evidence. So we either have strong evidence or we don't. So for this last example, we have 5 different pairs of hypotheses. We have to indicate which ones are not legitimate and then explain why. And all of these work for both cases, whether you're AP or dual credit, they'll work. So they're either not legitimate for both or they're legitimate for both. It's not like, well, for dual credit, it's this. No, they're the same across the board. So for A, what do we think? Is this legitimate or not? Well, the equal to part's okay, but this one, this is our problem right here, like you said. So it must only be greater than. Remember, for the alternative, those are strict. Strictly greater than, strictly less than, are not equal to.
I would just think I would include all hypotheses.
Yeah. And you're not wrong in what you're saying. No, we must strictly be greater than. What about the next one? Is it legitimate? If we say no, then we gotta say what? And we think it's legitimate? It could be. But I'll give you all a hint. The signs are not the problem here.
It's X bar, X bar, it can't be the population.
There you go. We must use a population characteristic. X bar is a statistic from a sample. Next one. This one legitimate.
Yes.
Yep, it's legitimate. We're good. What about the next one?
Oh, we got different numbers.
Different numbers, perfect. Gotta use the same numbers. And the last one. Come on. That's right.
What is it?
So it's no because the null says not equal. Remember,
That can work. Oh, it can only be equal, greater than or equal, and less than or equal.
that's right. If it's not equal, then it's gotta be over in the alternative. We're done?
I got a question too, but it's not.
Short day today. And for AP, I think you'll have like 6 problems, maybe 5. Can't remember.